Hello everyone, let's analyze. So today we're going to talk about properties of the derivative and higher order derivatives. So a few of the basic properties we'll go over. Let f and g map an open set of Rm to Rn. Suppose that both differentiable at x naught in the domain. Then the differential operator, in other words the operation of mapping a function to a function evaluation, is linear. In other words, the derivative of a linear combination of two differentiable functions at a particular point is a linear combination of the derivatives of each at those points. So of course this is a property that you're familiar with, the regular derivative you learned about in Real Analysis 1. Now if n is equal to 1, then it makes sense to multiply f times g and we get the product rule. Similarly, if n is equal to 1, then you can divide them so long as g at x naught is not 0. And we can compute the derivative there using the quotient rule. Because f and g for these last two bullets are real valued, we can actually look at the proof from Real Analysis 1 for these results and extrapolate it here, replacing absolute values for x naught and x in the domain with norms. But the proof is the same. The first bullet you actually prove in your homework. So we have the fact that the differential operation is linear. We have the product rule. We have the quotient rule. What are we missing? The chain rule. What if we take the derivative of a composition of functions? So f maps an open set of Rm to Rn. The image of the domain U is contained in the domain of G, and G maps it to Rk. So if f is differentiable at x naught, g is differentiable at f of x naught, then the composition is differentiable at x naught, and the derivative at x naught is given by the familiar chain rule. The derivative of g at f of x naught times the derivative of f at x naught. So let's prove this statement. Okay, so let's prove the chain rule. So I'll keep my hypothesis written here just to remind us. And our goal is to show that the composition is differentiable and the derivative is given by the chain rule formula. Now, for simplicity of notation, let's give some short names to our derivative matrices. We'll let AF be the derivative of f evaluated at x naught, and that is a n by m matrix. We'll let AG be the derivative of g evaluated at f of x naught, and that is a k by n matrix. And we'll let AH be the product of AG times a subscript f. Of course, this is k by n, n by m. My inner dimensions match. And my outcome is a k by m matrix. So then this goal, to show that this is differentiable, means I need to show it satisfies the definition of the derivative. So my goal can be restated as prove that the limit as x approaches x naught of my change in h minus my potential derivative matrix times the change in x divided by the change in x in norm equals 0 in the limit. We know from the statement of our hypothesis that f is differentiable and g, oh, that should be a g. G is differentiable at f of x naught. So let's rewrite this in terms of f of g, f and g. So let's take a look at the numerator. Since h is a composition, this is g of f of x minus g of f of x naught minus, remember, AH is defined to be AG times AF times X minus X naught. This is equal to, well, the same thing, but I'm going to add 0 in the form of adding and subtracting the same thing. So I added the derivative matrix of G at f of x naught times the difference, and then subtracted the same thing. Now I did that because as x approaches x naught, f of x approaches f of x naught. How do I know that's true? Well, f is continuous. How do I know that's true? Because f is differentiable at x naught. And as x approaches x naught, this minus this derivative, when I divide by f of x minus f of x naught, I should get that that limit is 0. Here, if I factor out ag, I get exactly the numerator of the derivative limit for f. So we can kind of see that we're on our way to showing that this entire limit, when I divide by x minus x naught, is going to give me 0. But of course, there are some details that we need to take care of. So first, let's split up what looks like a derivative of g statement, numerator, and what looks like the numerator of a derivative of f statement. So the triangle inequality says this is less than or equal to Notice that there's an AG and an AG in both terms, and because they're a matrix, they can be factored out. Now, this term here, because I have a matrix times a vector, this term here, this matrix times this vector, is less than or equal to the norm of the matrix times the norm of the vector. So we've broken this down in a way that this looks like the numerator of the derivative statement of g. Right? It kind of looks like this numerator, but for the differentiability of g at f of x naught. Of course, the difference is, right, I don't just have some vector y approaching f of x naught, I have f of x. Now, of course, f of x will approach f of x naught because of the continuity of f, but some care must be taken to ensure that we don't do anything silly like divide by 0. And this looks just like the numerator of the derivative statement of f, multiplied by some constant. So, what do we know? Now, we know that the limit as x approaches x naught of f of x minus f of x naught minus the matrix times x minus x naught, the derivative matrix, divided by the norm of x minus x naught is equal to 0. Right, we know that's true because that's the definition of the fact that the function f is differentiable at x naught. Now, our goal is to show that this is true, right? Now, to show that a limit is true, we're going to have to break out our epsilons and deltas. So let's go ahead and state what the epsilon is for this. Of course, it's arbitrary, right? I got to prove that I can make this arbitrarily small if I say the limit is 0. So let epsilon be some arbitrary positive number. Okay, right, and this is the beginning of proving our limit statement for this, right? For any epsilon, there exists a delta such that if x minus x naught is small enough, but not 0, then this fraction is less than epsilon, right? That's what we're going to be working towards. Now, I know that this limit is 0, right? That's a given. I would like to make this term, when divided by x minus x naught, small. So I know that for this, there exists a delta. Now, I'm going to need to consider the limit of the derivative of f. I'm going to need to consider the limit of the derivative of g. I'm going to need to consider the limit in the continuity of f, because I need f of x naught to approach f of x. So there's probably going to be a few epsilons and deltas flying around. So let me go ahead and mark this as delta 1. There exists a delta 1 such that the ball centered at x naught with radius delta 1, remember this is an open ball as we've defined it, is contained in U. And, by the way, how do I know that I can find a ball around x naught that's contained in U? That's because U is open. And if x is in that ball, but not at the center, then this quotient is less than, well, whatever I want, right? Or rather, for whatever I want, there exists a delta 1 that'll guarantee whatever I want. Okay, what do I want? Well, I want this numerator divided by x minus x naught to be less than half an epsilon, because I'm adding two things. Of course, I'll have to divide that by the norm of this, so that this entire term is bounded by epsilon over 2. So I'll get epsilon divided by 2 times the norm of AG. Now, what if the norm of this matrix is 0? Well, just to guard against that, we'll add a positive number, like 1. I could have added 72, but I picked 1. Okay, so what else do we know? We know that in the limit as y approaches f of x naught, g of y minus g of f of x naught minus the derivative matrix times y minus f of x naught divided by the norm of y minus f of x naught equals 0. So there exists another delta, delta 2, such that the ball centered at f of x naught, delta 2, is contained in V. Right? I can find such a ball because V is open, and well, that's actually the definition of it being open. And if y is in the ball centered at f of x naught with radius delta 2, but not equal to f of x naught, right? Remember, in the limit, we're concerned with what happens as y approaches f of x naught rather than the value of y at f of x naught. Then this quotient is less than, now, well, again, is less than whatever I want. Well, what do I want? Remember, let's go back to my goal. My goal is to make this quotient arbitrarily small if x and x naught are sufficiently close to each other. The numerator can be split into this term and this term. Now this term, when I divide by x minus x naught, we've guaranteed I can make it less than half an epsilon. So I need to make this term, when divided by x minus x naught, less than half an epsilon. And this term here looks like the numerator, except that here I'm considering some y in the domain of g. Now, of course, f of x is in the domain of g, right, by hypothesis, by assumption. But here, y is just any vector approaching f of x naught. So what do I have to make this less than? Well, you know what? I'm not sure yet. So let's just call this epsilon delta, and we'll just say to be determined. If y is in this ball, centered at f of x naught with a radius of delta 2. Now here I said except for the center, right? Except for f of x naught. That's because, again, when you take a limit, you're interested in what happens as y approaches f of x naught, not when y is equal to f of x naught. However, remember, our goal is when I divide this by x minus x naught, I want it to be arbitrarily small. And there's no way of me knowing whether f of x is going to equal f of x naught for x close to x naught. In other words, I don't want to divide by 0. So let me just rearrange this statement where I'm going to allow y to possibly be the center. Then the numerator g of y minus g of f of x naught minus the derivative matrix of g times this difference y minus times y minus f of x naught is less than epsilon times the denominator, which is the difference of y minus f of x naught. Now, if I let y possibly equal the center of this circle, then I'd have to say less than or equal to, because if y is equal to f of x naught, then I would get 0 on both sides. By the way, let's just remind ourselves what this means. This just means that the norm of y minus f of x naught is strictly less than delta 2. Now, I would like to say that when we broke down the numerator of our goal limit, right? When we broke down this numerator, we're able to bound it by 2 terms. Okay? I'd like to say this term, right? I would like to bound this term using this statement here. Now, in order for me to do that, I would have to say that f of x is within delta 2 of f of x naught. In other words, I need f of x to be in this open ball. Okay? Well, I can do that. In fact, I can make f of x as close to f of x naught as I like because f of x is continuous at x naught. So I know f is continuous at x naught because it is differentiable at x naught. So there exists a third delta such that the ball centered at x naught with radius delta 3 is contained in U. Of course, I can make sure that I pick a delta 3 small enough to be contained in U because U is open. And if x is in this open ball, but not x naught, then f of x minus f of x naught is less than delta 2, right? Because I need to put f of x inside of this ball, right, in order for that first term of my bound to be bounded. Of course, And that's exactly what this is saying. This is saying that f of x is within delta 2 of f of x naught. Now, I want f of x to be in this ball, which means x needs to be in this ball. Now, I also want this statement to be true, which means I want x to be in this ball centered at x naught. So there's two balls both centered at x naught that I want x to be in. So let me just pick the smaller of the radiuses, smaller the radii. If x minus x naught is less than delta, which is, again, the smaller of delta 1 and delta 3, then, and now we come back to our goal. Right, now we're going to show that we can make this arbitrarily small. So then our quotient can be bounded by this quotient plus this quotient. Okay? Now, if x is within both delta 1 and delta 3 of x naught, then that means, well, it means that this term is less than the norm of this matrix AG times epsilon divided by 2 times the norm of AG plus 1. And this numerator is less than or equal to my epsilon tilde times f of x minus f of x naught divided by x minus x naught. Okay. Now, how do I know that this numerator is bounded by epsilon tilde times this? Well, because x is within delta 1 and delta 3 of x naught, that means f of x is within a delta 2 radius of f of x naught. That means f of x satisfies this condition, which means this is true for y equal to f of x, which is exactly what we have written here. Now, how do I know that this numerator is bounded by this numerator? Well, because x is within both delta 1 and delta 3 of x naught, I know that x satisfies this condition, which means f of x is contained in the delta 2 ball of f of x naught. That means f of x satisfies this condition, which implies that g of f of x, in other words, if I let y be f of x, this is true, which is exactly what I have here. Now, f of x minus f of x naught divided by x minus x naught, that looks an awful lot like an approximation of the derivative, right? Rise over run, or the norm of rise over the norm of run. So that should give us an idea. This is equal to epsilon tilde f of x minus f of x naught minus AF times x minus x naught plus AF times x minus x naught divided by x minus x naught plus epsilon over 2 because, well, the norm of AG is less than the norm of AG plus 1. So in fact this would be, and it's strictly less than, so this would be less than because I'm replacing this with something bigger than it, epsilon over 2. So I can split this up using the triangle inequality. So this becomes less than or equal to epsilon tilde f of x minus f of x naught minus AF x minus x naught plus AF times x minus x naught divided by x minus x naught plus epsilon over 2. Now, I know that this f of x minus f of x naught minus the derivative matrix times x minus x naught divided by x minus x naught, I know that that's arbitrarily small, and in fact, if x satisfies the deltas given, then we've already given a bound for that. So this is less than epsilon tilde times epsilon divided by 2 times the norm of AG plus 1 plus the norm of AF, right, times x minus x naught divided by x minus x naught, so I just get this norm, plus this epsilon over 2. Now, remember, epsilon tilde was a epsilon to be named later. Well, I want this entire thing, I would like it to be less than epsilon over 2. So this equals epsilon if epsilon tilde is epsilon over 2 times the reciprocal of this. And I've proven my result. Epsilon was arbitrary. There's a delta, and if x is sufficiently close to x naught, then my derivative quotient is strictly less than epsilon. So let's see the chain rule in action. Let's consider an example, a function f that maps three-dimensional vectors to two-dimensional vectors, and g is a map from R2 to R3. So let's do two things. Let's compute the composition. In other words, let's express the composition as just a function of x so that we can take the derivative directly. And then let's compare that to the derivative of g evaluated at f of x naught times the derivative of f evaluated at x naught, where x naught is 1, negative 1, 2. So we'll confirm the chain rule at a particular point. So the composition h of x, which is equal to, right, I'm going to use g essentially as my scaffold, but I'm going to replace x1 with f1, x3 with f3, because it's going to be g of f. So I'll get 2 f1 of x squared times f3 of x, f1 of x plus f2 of x, and f2 of x. And then let me plug in what f1, f2, and f3 are, of course, defined here. So I'll get 2 times f1, which is x1 plus x3 squared, I'm sorry, that should be x2 because G maps R2 to R3, so there is no x3. And this would be f2 times 2, so 2 squared, x1, x2, x3, f1 plus f2, and then f2, which is 2, x1, x2, x3. So now that we have the composition just as a function of the components of x, we can just compute a derivative. Because H maps vectors in R3 to vectors in R3, we're going to get a 3 by 3 matrix. So the derivative of my composition evaluated at x naught is, let's see, plug in the 1, carry the 2, I get negative 120, 72, negative 84, negative 3, 4, negative 1, negative 4, 4, negative 2. Now, of course, the chain rule says I could have also computed this by computing the derivative of g at f of x naught, computing the derivative of f at x naught, and multiplying. So let's do that as well and see that we get the same thing. So there's the derivative of f as a function of x, and here's the derivative of f at x naught. Plug in my values for x naught. Sorry, I'm supposed to plug in my values. That would be negative 4, 4, negative 2. Now let's take the derivative of g. And let's compute the derivative of g at f of x naught. By the way, the derivative of g f of x naught is 3, negative 4. And so if I plug in those two values into x1 and x2, I would get negative 48, 18, 1, 1, 0, 1. And in fact, if I multiply this matrix on the right by this matrix, I get exactly this. By the way, how did I do all of these computations? Did I do it on my head just now on the fly? No. Let me show you how. So here I wrote a quick MATLAB script to demonstrate our example. I have the derivative of the composition of g and f at x, and I wrote it out entry by entry. I defined x naught and computed at x naught. That gives me this first matrix. Then I defined f and plugged in the derivative of f as a function of x and evaluated at x naught. That gives me this. I also computed f of x naught so that I can compute the derivative of g of f of x naught. And then I took the product of this matrix multiplied on the right by this matrix, and I got this, which we can confirm is this. But just to make sure, I subtracted this term that says this should be 0. Well, this should be 0, and in fact it is. If it weren't, that would mean the chain rule is not true. Well, it would mean I actually made an error in my code somewhere, because the chain rule is true. I proved it. So as a corollary to the chain rule that we just proved, under the same hypothesis as the chain rule, if I want to take a a partial derivative of a particular entry of h with respect to a particular variable xj, then I can do it by taking the transpose of the gradient of the ith entry of g times the partial derivative of f at xj. Now, why is this true? Because the derivative of hi with respect to xj is the ijth entry of a matrix, specifically the derivative matrix of h. And that matrix is the product of the derivative matrix of g at f of x naught times the derivative matrix of f at x naught. And so that entry is going to be a row of the derivative matrix of g times a column of the derivative matrix of f. And that's exactly what I have. This represents a column of the derivative matrix of f, and the transpose of this is a row of the derivative matrix of g. And that's how we get this formula. So next we're going to tackle the mean value theorem. If you look back to the mean value theorem from Real Analysis 1, you might remember it as a statement that said the average rate of change equals the instantaneous rate of change at a particular point. If you thought about it in the analogy of velocity, it means your average velocity equals your instantaneous velocity at a particular point. If we're going to be dealing with a multidimensional space, then we need to figure out how can we consider a point C between two other points U and V. And so we can do that by taking a convex combination. So if U and V are vectors in a vector space, then a convex combination is, well, it's just a linear combination where my coefficients sum to 1. So because they sum to 1, I can actually just represent it by alpha and 1 minus alpha. Of course, that sums up to 1. So C of alpha is a vector on the line containing, or on the line joining U and V. When alpha is 0, I get U. When alpha is 1, I get V. And when alpha is between 0 and 1, I get a vector on the line that joins U and V. That allows us to define a line segment, a open or closed line segment that joins U and V. So if alpha is strictly between 0 and 1, then I get a vector strictly between U and V. In other words, on the line segment joining U and V. And of course, if alpha is allowed to be 0 and 1, then I would add U and V to that set. Now, U, a subset U of V, is a convex subset of V if for every two elements of U, the convex combination is also contained in U. So now we can state the mean value theorem. Let F map an open set U in Rm to Rn, and suppose it's differentiable on U. Notice here I'm saying that it's differentiable on the entire domain U. Then for any interval x, y contained in U. Now remember, when I say an interval, what I mean is the line segment joining x to y. If n is equal to 1, then the difference between f of y minus f of x is equal to the derivative at some point c in the open interval from x to y times y minus x. Now, if n is greater than 1, then there are n vectors, c1, c2 through cn, each of them in the open interval x to y, such that the mean value theorem is satisfied one at a time, right, for each entry of f. Of course, f has n entries because it maps Rm to Rn. So let's prove this statement. So let's prove the mean value theorem. We'll consider first the first bullet when n is equal to 1. So define a function h that maps the closed interval 0 to 1 to R by h of alpha is equal to f of the convex combination alpha v plus 1 minus alpha u. So let's just note that when alpha is 0, I get 0 times v plus 1 times u, or u. And when alpha is 1, I get 1 times v plus 0 times u, or v. So again, this is the line that as alpha goes from 0 to 1, goes from u to v. Now since f is differentiable, and this convex combination is differentiable, then by chain rule, h is differentiable. Remember that the convex combination from u to v remains in the domain u. That means that h of alpha is also continuous. Now, this is a mapping from a number to a number. So we can actually apply the mean value theorem for real valued functions on real domains. In other words, the real analysis 1 mean value theorem, right? We've put ourselves firmly in the camp of real analysis 1. There exists a gamma contained in the open interval 0 to 1 such that h of 1 minus h of 0 divided by 1 minus 0 equals h prime of gamma. Now, of course, h prime of gamma, according to the chain rule, is the derivative of f at gamma u plus 1 minus, that would be a v, 1 minus gamma u times the derivative of this with respect to gamma, or with respect to alpha and evaluated at gamma, times v minus u. Now, we're going to call this C. Remember, h of 1 is f of v. H of 0 is f of u equals the derivative of f evaluated at C times v minus u, which completes our proof of the first bullet. Now, for the second bullet, we just apply the result from 1 to each fj of x, for j is equal to 1 through n, because the codomain is within an n-dimensional space. And that completes the overall proof. So let's discuss higher order derivatives. Now, a higher order derivative, like a second derivative or a third derivative, if we think back to calculus 1, a second derivative is just the derivative of the derivative function. So let's review. Let f map the open interval a to b to R. Let it be differentiable on the entire open interval. Well, for each x naught in the open interval, the derivative at x naught is a number. In R. Okay. So if I isolate a point and take the derivative there, f prime of x naught is a number, right? We put it into the language that we've been discussing. It's a 1-by-1 matrix, otherwise known as a number. Now, how is that related to a linear operator? Well, if I took that number and multiplied by x, then it would be a linear operator defined by this number. The derivative function f prime is a mapping from the domain where I'm differentiable to R. So f prime of x naught is a number. At each x in AB, I get a different number. Well, that's a mapping from the interval AB to R. Now let's let f map an open U in m-dimensional space. We'll map it to n-dimensional space, and suppose it's differentiable on the open interval U. Right? So again, notice I have the same setting, but now I'm just generalizing the dimension. Here I was in one dimension, and here I'm generalizing. So for each x naught in my open domain, the derivative of f at x naught is, and I'll put in parentheses, equivalent to a matrix. In R n by m. Okay, I say equivalent to a matrix because, as we said in the definition of the derivative, we can also think of it as a linear mapping from Rm to Rn. But every linear mapping from Rm to Rn can also be thought of as a matrix. So just the way f of x prime is a number, and that number can correspond to a linear mapping by multiplying f prime of x naught, that number, times x. Similarly, this matrix corresponds to a linear mapping by multiplying the matrix times the coefficient of a vector that you're operating on. So A is a matrix, and it corresponds to a linear mapping A times x. df of x naught is a matrix, and it corresponds to a linear mapping of this matrix, or the matrix corresponding to it, times some vector in U. And of course, it takes a vector in U to a vector in Rn. So again, hopefully we see the analogy. F of x prime is a number. The derivative of f at x naught is a matrix. And the derivative function maps U to, right, well again, for each x naught, or for each number in U, I get a matrix. Now just a quick parenthetical. A matrix that is n by m, right, is every matrix with n rows and m columns. But again, every matrix corresponds to a linear map from Rm to Rn. So we can say it's equivalent to, right, the set of, right, so the set of all linear maps from Rm to Rn. Okay? Every matrix represents or corresponds to a linear map. So now I can consider this function from U to Rn by m. Right? Just like I considered f that maps U to Rn, here I have another function that maps U to Rn by m. Now, by the way, I can think of Rn by m as a vector space. Right? A linear combination of n by m matrices is a n by m matrix. So it's a vector space. It's of dimension n times m. But I can also consider whether this is differentiable. If df is differentiable, at some x naught in the domain, what does that mean? That means there exists a linear mapping from U, which is contained in Rm, to Rn by m. And we denote it the derivative of f at x naught, or the second derivative of f at x naught. Now remember, the first derivative, right, it's equivalent to a matrix, and a matrix is a linear map from Rm to Rn. In other words, the derivative at a point, right, is a linear mapping from the domain to the codomain. So if df is differentiable, the derivative at a point is a linear mapping from the domain to the codomain, right? Because the domain of the derivative is u in Rm, and the codomain is Rn by m. So just to recap, the second derivative at a particular point is a linear mapping from Rm to Rn by m. Now, as we stated before, Rn by m can be thought of as the set of all linear maps from Rm to Rn. Does that mean the set of all linear maps from Rm to Rn by m can be thought of as rectangular prism matrices? Well, yeah, in a sort. In fact, if I take the linear map and apply it to a basis of this, represent each outcome and a basis for this, then I can actually build myself a sort of three-dimensional matrix. So because the second derivative of f at x naught maps some u in the domain, right, because it's a linear mapping from u, so it maps some u in the domain, which is in Rm, to a matrix in Rn by m. That's an m there. And it does so linearly then d squared f of x naught of u is in Rn by m, right? It's a matrix, again, which is equivalent to saying it's a mapping from Rm to Rn, right, by matrix multiplication. That's how the mapping occurs. So because it's a matrix of size n by m, I can multiply it by a vector in Rm. So if v is in Rm, d squared f of x naught U. So this is a matrix, right? This is a n by m matrix, which again represents a linear mapping from m dimensions to n dimension. So let's map V in m dimensions. Right, this equals a vector in Rn. So notice that this is linear in two different ways, right? This maps U to a matrix linearly. In other words, I'm linear in the U argument. Also, because when I multiply by V, I'm just multiplying a matrix times V, that's also a linear map. So I have something that's linear in U and linear in V. So let's define B. Of course, B is going to depend on x naught. And let's let it be a function of both U and V, and it's defined to be the second derivative evaluated at x naught. And then I'm going to map a vector U to a matrix and then multiply that matrix times V. And as I mentioned, that outcome is a vector in Rn. So because this mapping, it maps two vectors in Rm. So because this is linear with respect to U, because remember the second derivative at x naught is a linear mapping from a subspace of Rm to a matrix, it's linear with respect to U, and because the operation on V is just a matrix times V, it's linear with respect to V. Therefore, Bx naught maps two vectors from Rm to a vector in Rn is a bilinear map. Now, what's a bilinear map? Well, a bilinear map is just a function of two vectors that maps to a third vector, and the function is linear with respect to each of its argument vectors. Okay, so a bilinear map is just a mapping of two vectors to one vector that's linear in each argument. That is, if U, V, and W are vector spaces, and B maps a vector in U and a vector in V to a vector in W, then we say it's a bilinear map if it's bilinear with respect to each argument. In other words, it satisfies the definition of a linear map for each argument U or V. Right? So as noted, the second derivative represents a bilinear map. By the way, the third derivative would represent a trilinear map, a map that's linear in three arguments. The fourth derivative represents a quadlinear map. You get the idea. Okay, so now that we've seen a formal definition of what we mean by a bilinear map, let's just quickly review how the second derivative can be thought of as a bilinear map. Now, remember that the second derivative is a linear mapping from my domain in Rm to a matrix of size n by m. But remember that a matrix of size n by m itself is a linear mapping from Rm to Rn. Right? Remember we wrote that down here. Matrices of size n by m represent linear maps from Rm to Rn. How do you carry out the linear map? Well, by matrix vector multiplication. Right? Because a n by m matrix can be multiplied by vector in Rm to get a envelope in Rn, and that mapping is linear. So I have a linear mapping twice over. Right? The second derivative maps linearly a vector in Rm to a linear mapping from Rm to Rn. Because remember, a m by n matrix is equivalent to a linear mapping from Rm to Rn. Right, so that idea is crucial. That means the second derivative is a linear mapping of a vector in Rm to a linear mapping of a vector in Rm to a vector in Rn. And that is what's represented here. That is why we can think of the second derivative as a bilinear map, because it's a linear mapping to a linear mapping. So now suppose that n is equal to 1. In other words, suppose that f is real valued, right, which is say that its codomain is just the real line or one-dimensional. Then b of x naught maps Rm by Rm to R, right? I have a bilinear map from Rm by Rm to R. Well, in fact, I can actually think of this as a matrix, or I can represent the bilinear map by a matrix. So let U1 through Um be a basis for Rm. Of course, we oftentimes take the canonical basis of E1 through Em. Remember that Ej is the vector of all zeros except for a 1 in the jth position. But let's just take an arbitrary basis for Rm. Let's let U, right, of course U is going to be in Rm, so it's a linear combination of these. Alpha I Ui from I equals 1 through M, and we'll let V also be in Rm to say that it's a linear combination of the same basis vectors. Beta j uj from j equals 1 to M. Well then, B of uv, because it's bilinear, I can actually factor out the summation and the scaling to get alpha I, beta j, bx naught of ui, uj, and this is from I equals 1 to m, j equals 1 through m. Now I was able to extract my summation and my coefficients by using the bilinearity property. And in fact, this is equal to alpha transpose, my matrix that represents my bilinear map, times beta, where this matrix M is equal to the bilinear map of U1 and U1, U2 and U1, UM through U1, the bilinear map from U1 through UM, and the bilinear map from UM through UM, with dot dot dots in all the right spots. Of course, alpha is just the vector whose entries are my alpha coefficients, and beta is the vector whose entries are my beta j coefficients. So in fact, I get exactly this. Notice this makes sense because I have two arguments, alpha, which is equivalent to u, in the sense that every vector u in Rm has a unique set of coefficients in a particular basis. So whether I'm talking about u or alpha, right? They're equivalent given a basis. In fact, if this is the canonical basis, then alpha is just the entries of U. And similarly, beta are the entries of V if this is the canonical basis. But I pick an arbitrary basis just to show the generality of this. So if I take a vector transpose times a square matrix times the vector beta, right, I get a number, which makes sense because this is a bilinear map to R since n is equal to 1. And if I isolate beta, it's linear with respect to this argument, and if I isolate alpha, it's linear with respect to this vector argument. That means the second derivative of a function that maps Rm to R can be represented by a matrix. And in fact, that matrix has a name. It's called the Hessian. Let's take a look at it. So for a real valued function, in other words, a function that maps m-dimensional vectors to numbers, if it's differentiable twice, then the matrix representation of the bilinear map, right, as we pointed out, the bilinear map can be represented by a matrix. If we compute this matrix in the canonical basis, then we'll get this derivative, right? The jk entry is the second derivative of f, first with respect to xk and then with respect to xj. This is also called the Hessian matrix. By the way, let me mention one application of the Hessian. Imagine that you want to minimize some function from Rm to R. Then you might be aware that if your function is differentiable and your min and max occurs in the interior, then the derivative would be 0 there. If the derivative is 0 and you want to apply, for example, a root finding algorithm like Newton, then you would need the derivative of the derivative, also known as the Hessian, in order to apply a method like Newton's method. So when is the Hessian symmetric, or when is the matrix representing the bilinear map symmetric? Well, suppose that F maps a subset of Rm to Rn, is differentiable twice on U, and the second derivative function, which, remember, it maps U to a linear mapping from M to n by m, which also can be thought of as R n by m by m. Now, suppose that the second derivative is continuous on U. Then, for each x in the domain, I can take the derivative first with respect to xi and then with respect to xj, or with respect to xj first and then with respect to xi, and get the same thing. Now, we don't have the time right now to give a thorough proof of the symmetry of mixed partial derivatives. I would like to give a sketch or an idea of how the proof works. So the idea is that it doesn't matter whether I take a derivative in one direction first and then the second direction after, or if I switch the directions that I take my partial derivative. Now, since we've isolated in the theorem a single fk, right, that maps Rm to R, and two components of x, the ith and the jth, then if that's what I'm looking at, then let's just consider a function f that maps R2 to R, because we're just looking at f of xi and xj at the kth entry. So in this setting, what it's saying is, if I take the derivative in the x1 direction and then the derivative in the x2 direction, I'll get the same thing as if I took the derivative in the x2 direction and then the x1 direction, if the hypothesis of my theorem is satisfied, of course. So just to give an idea of how this would work, let's consider the function r of h k. And in my picture, I have x, and then I move in an h direction, right, which we should recognize from the definition of partial derivatives, that you're taking a difference in one direction. And then we go in the x2 direction by an amount of k. So we'll let r be the difference between f evaluated here minus f evaluated at these two corners, plus f evaluated here. And of course, the idea is to let k and h shrink so that this rectangle collapses to this point here. And the idea is to show that if I take my derivative in this direction and then this direction, I'm going to get the same thing as if I went this direction and this direction. So notice that if I were to keep these two isolated and consider these two, I have a difference, right, this minus this, right? I have a difference in the x2 direction, and then here I have a difference in the x2 direction. Similarly, if I look at these two, if I look at these two, I have a difference in the x1 direction, and if I compare these two, I have a difference in the x2 direction. So because of these finite differences, I can actually apply the mean value theorem. There exists a C such that RHK divided by the difference H is equal to the derivative of f and the first component evaluated at C. At these 2 points, right? So C is somewhere between x1 and x1 plus h. So C is some point here. But what I did is I took the difference from here to here and then also the difference from here to here. So here's C over here. Now again, I have a difference function, and because my function is twice differentiable, I can apply the mean value theorem again. So I can say now there exists a, right here in the x2 component is my difference, there exists a d in the interval x2 plus k, so that this is the derivative with respect to x2 of the derivative of f with respect to x1 evaluated at C and D. So D is somewhere along here, D and D. Right, so I took a difference in this direction and then a difference in this direction. And so here I have the coordinates C and D. And at that coordinate C and D, the derivative with respect to x1 and then a derivative with respect to x2 is equal to this ratio, right? And C and D is somewhere inside my rectangle. Now notice I looked at this difference first and then this difference. Now let's look at this difference and then this difference. So again, by the mean value theorem, there exists another d, we'll call it d prime, between x2 and x2 plus k, such that RHK divided by k is equal to the derivative of f with respect to x2 evaluated at d prime minus the derivative at x2 at x1 comma d prime. So again, I'm looking at here, and I'm looking at the differences where x2 plus k minus x2, x2 plus k minus x2. I apply the mean value theorem to get this for some point d prime. Of course, d prime is going to be a different point. Here's d prime. I'm also going to get a c prime, and here's my c prime d prime coordinate. Again, another coordinate inside my rectangle, different from this. So again, because now I have a difference in the first component, there's a c prime in the interval x1 plus h, such that RHK divided by KH is equal to the derivative with respect to x1 of the derivative with respect to x2 at c prime d prime. So that means the derivative here with respect to x1 first and then x2 equals the derivative here with respect to x2 first and then with respect to x1. Now, not only do I know that these second derivatives exist, I've also supposed in my hypothesis that the second derivative is continuous. So then, as k and h go to 0, the coordinates c and d and the coordinates c prime and d prime converge to the coordinate x1 and x2. And because they're equal, they're also going to be equal in the limit as k and h go to 0. And it's going to assume the value of the limit as k and h go to 0 because of the continuity of the second derivative. Therefore, the second derivative with respect to x2 and then x1 at x, which is the coordinate x1 and x2, equals the second derivative with respect to x1 first and then x2. Okay, and we have our result. Okay. Of course, the details that are left out is how exactly I set up my mean value theorems, but again, because we have all the differences that we need kind of recorded in this R function, we can apply the mean value theorems as many times as we need. And that's it for today.